In example 5, we know that the standard treatment for a particular disease is successful 2/5 of the time. So the probability of success is 2/5 of the time. Well, some doctors undertaken research and they think that they've produced a new drug which is more successful than this. And in order to test this claim, the doctor is trialing the drug on 20 patients, and he or she manages to cure 11 out of the 20 patients. So it certainly looks at first glance that 11 out of 20 is a high proportion than 2/5. So the doctor is claiming that the new drug is more effective. So we're going to test at the 5% level whether this claim is true or not. So we're going to start off with defining a random variable. So the random variable is going to be our test statistic, which is the data that we're going to get given in order to test this claim. So the data that we get given is the number of patients cured out of a sample of 20. So next we're going to write down what distribution does this follow. Well, you can kind of think about this as doing 20 trials, and the probability of success on each trial is going to be, well, let's call it P because we don't know what that is for the new drug. So it's going to be a binomial distribution, 20 trials, and let's say P is the probability of the drug curing a patient, so the probability of success. So P is the probability of the drug being successful on a random patient. So next we need to write down what our null and alternative hypotheses are. So our null hypothesis is that the drug is no better than the existing treatment, and the probability of the drug being successful is just 2/5. The alternative hypothesis is, well, the doctor thinks that the new drug is more successful. So that would mean the probability of success is greater than 2/5 for this drug. So next we're going to say, well, if H0 is true, then actually X, which is the number of successful treatments out of the sample of 20, would follow a binomial distribution with 20 trials, and if H0 is true, the probability of success would be 2/5. So it's worth noting at this point that we would expect, if this is true, so if H0 is true, we would expect 2/5 of the 20 to be successful. So 2/5 times 20, so 8 successes. Okay, so at this point I'm also going to write down what values of X are going to try and help support the doctor's claim. Well, if the doctor thinks the probability of success is greater than 2/5, then we would expect significantly more than 8 patients to be cured. So that means that large values of X support H1. And that by large, I mean significantly more than 8. So this tells us that we're doing a right-tailed test. So the critical region would be for the large values of X in the right of the distribution. So we're actually going to look at two different ways of going about this and making a conclusion. We're actually going to start with the way that we aren't going to do, but it's actually related to the critical region. So we're going to start with the critical region method, because that's what we've been doing before. And then we'll look at a slightly more efficient method. So with the critical region method, you don't need to draw out the distribution, but I'm going to draw it so I can try and explain what we're doing. So along the horizontal axis, I'm going to put X, which is the number of successes out of our sample, so out of 20. And on the vertical axis, I'm going to put the probability. So remember, this distribution is going to be under H0. So if H0 is true, this is what our distribution would look like. Binomial 20 2/5. So we don't really, I'm only using the distribution to try and help us explain it, so I'm not going to draw it accurately. We could have 0 successful treatments, so none of them get better, only one of the patients could get better, 2 of them could get better, etc. Now we're interested in the region around about 11 because 11 got better. So I'm going to draw in, remember the highest probability would be around 8, but I don't need to draw that in our diagram because we're looking at the right of the distribution. So I could have 10 of them could have got better, 11, 12, 13, etc., all the way up to all 20 of the patients getting better, which would have a really, really small probability. So let's have a go at trying to work out this critical region. So let's try a probability of x being greater or equal to 10, for example. So let's work out what that probability is here. So we're going to have to do 1 minus the probability of x being less than or equal to 9. Remember, that's because all probabilities add up to 1. So if we want just 10 and above, we have to take away from 0 up to 9. So to get this probability, we're going to use the cumulative binomial function on our calculator. So we go on statistics, and then distribution, binomial, cumulative. We want the probability of x being less than or equal to 9. Remember, that adds up all the probabilities from x equals 0 up to x equals 9. Number of trials is 20, and the probability of h naught's true is 2/5. We always do the probability of h naught's true. And then we have to do 1 minus this probability here. And if you work that out, you get that that's equal to 24.5% roughly. So that probability is too big. Our critical region the probability of being in our critical region has to be no more than the significance level, and our significance level is 5% in this case. So that's too big. So we're going to have to try a smaller critical region. Let's try greater than or equal to 11. So probability of x being greater than or equal to 11, we'd have to do 1 minus the probability of x being less than or equal to 10. And if you work that out, you'd get 12.8%, which is still too big. So that probability there is 12.8. So let's try the next value along. Let's try greater than or equal to 12. So we'd have to do 1 minus the probability of x being less than or equal to 11. And that's 5.7%. So we're getting closer to 5%, but it's still too big. So we're going to have to try greater than or equal to 13 and see what that percentage is. So the probability of x being greater than or equal to 13 is 1 minus the probability of x being less than or equal to 12. And that gives us 2.1%. So this is the first probability that's less than 5%, and it's as close to 5% as we can get. So that means that our critical region, in this case, is x is greater than or equal to 13. So remember, what that means is if x is 13 or larger, then we've cured enough patients in order to reject H0, in order to say that our drug is more effective. So in this question, we cured 11 out of the 20 patients. So we observed x equals 11. So we've got to work out, are we in the critical region? Well, we're not in the critical region here because we needed to cure 13 or more. So we can say x equals 11 is not in the critical region. So do not reject H0. Remember, our conclusions are either reject H0 or do not reject H0. So that's the key word in this case here. And then our final step is to conclude in context. Now, we always conclude in terms of our alternative hypothesis. So remember, someone has asked us to try and prove whether their drug is more effective than 2/5 or not. So we've got to conclude about that alternative hypothesis. And the options are, we either have sufficient evidence or insufficient evidence to support the alternative hypothesis. So in this case, because we're not going to reject H0, we're going to say there's insufficient evidence to suggest that the new drug is more effective. So the key word here is we're saying there's insufficient evidence, and then we related it back to the alternative hypothesis, what we were asked to show. Now, it's really important to realise what I've not said is I've not said that the probability of the drug curing someone is 2/5. All I've said is that there's not enough evidence to suggest that the probability is more than 2/5. So I've related it back to the alternative. And the reason why I'm saying that is a little bit subtle, but because we had our H0 was 0.4, we could have repeated exactly the same hypothesis test, but with p is equal to 0.41, and we would have had the same conclusion. So a hypothesis test doesn't tell us that the null hypothesis is true or not. A hypothesis test only tells us, have we got enough evidence to support the alternative or to not support the alternative? So in this question, we weren't actually asked to find the critical region. And there's actually a nice, much easier to work out whether you can reject or do not reject H0, and it's called the p-value method. So the way the p-value method works is we can think about the distribution. Obviously, you don't need to draw it out. I'm just using it as a visual help. And we cured 11 out of the 20 patients. So basically what we've got to work out is 11 in the right 5% of the distribution? So what we're going to do is we're going to work out what's called the p-value. Now the p-value is the probability of being where you are or more extreme. And by more extreme in this case, we mean where we are or a larger value of x, because we want large values of x to support H1. If we were doing a left-tailed test, then we would do 11 or to the left, but we're doing a right-tailed test, so it's 11 or higher. So our p-value in this case is the probability of x being greater than or equal to 11. Just be really careful, it's not equal to 11, it's greater than or equal to, because it's a right-tailed test. So to work this out, we'd have to do 1 minus the probability of x being less than or equal to 10. And we get that probability is 12.8%. We'd already worked that out before. So remember, we're using this to try and work out, are we in the right 5% of the distribution? Well, because that 12.8% is more than 5%, we know that 5% has to be somewhere like that. We are not in the right 5% of the distribution. So we're going to say that because the p-value is greater than the significance level, so in this case it's 12.8% is greater than 5%, what that means is we're not in the right 5%. So we're not in the critical region. Okay, and we can work that out even without having to work out what the critical region is. We just know that. So we'd make the same conclusion before. As before, we said do not reject H0. And we'd say there's insufficient evidence to support the alternative hypothesis. It's worth thinking about what happens if the p-value is really, really small. For example, imagine we had a p-value of 1%. So this is just an example, completely separate to the example that we just did. So a p-value of 1% would mean that you're right in the final 1% of the distribution. So that would mean that if H0 is true, it's really, really unlikely that you're there. So because 1% would be less than 5%, in this case, if our p-value was 1%, that would mean that actually we are in the right 5%, and it would mean that 5% would have to be something like that. So if we were here and we only had 1% of where we are to the right, that would mean we are in the critical region. So if the p-value was 1% and the significance level was 5%, because 1% is less than 5%, we would actually reject H0 and would say there is enough evidence to suggest the alternative is true. So you can only reject H0 when the p-value is less than the significance level.